All right. Hopefully, did everybody make it? Should I like go search the rooms? Maybe yeah. I'll price. Okay, and nobody was next door because I sent everybody the wrong room too. Like a mess. Oh gosh, everything's a mess. There we go. All right, now it's fixed. Okay, we're streaming. So hi, so welcome to my class. Oh, one more thing. I'm gonna run out of power. All right. Apologies for the late start. So usually I like to start right on time, of course. We have a lot to cover for chemistry and the class and everything. I'll introduce myself. So my name is Marissa Shepard, and I do have a PhD, but you don't have to call me doctor or anything. Marissa is just fine. And what other? So email is the best way to communicate. So M Shepherd, and then just at Rogue. And then I forgot I do need to take attendance, but I'll get there in a second for the in-person people. And then was anyone trying to add the class? I feel like there was one person that was like trying to sneak in to my lab, and I was willing to accommodate, but I don't know if they're here today. Anyways. So let me pull up kind of the syllabus and, well, actually, I'll talk about some things because I really had I had a vision and it didn't really work, but I'll kind of explain. And so for the in-person folks, I assume you want like a traditional kind of very paper-based format, but what I was kind of having in mind and kind of exploring is I know like so many people like taking online classes. So what I was trying to do is like rebuild, and now this is like probably too much information for y'all, but like Blackboard is kind of a pain. And so I was like, okay, I'm going to start fresh, but I'll do it in my open math, and then I'll have it talk to Blackboard. But then I later discovered that like if you don't have my open math completely done, which I don't, because it's taking me a lot longer to do because nothing plays well. It doesn't want to be copied over. So then I didn't want to make a bunch of confusion. But that being said, I think there might be a way that I can get around it and have y'all like get a code for my open math to join in. But then like for the in-person people, this would just be like fun experimental stuff. And same thing for the online, like I'm not going to require any of the my open math, but the whole idea was that I would have like more practice so that you could kind of, I don't know why that's not filling. Thank you. Yeah, because I was like trying to make it like more robust and then have all these like quizzes and so forth, right? Where you could kind of keep practicing online just as another way to like practice and learn like because that's something that people always ask me, like in person, is like, how can I practice more? What can I do? And I would love to have another like resource. Welcome. Sorry, I was so confusing, and we changed rooms at the last minute. I don't know if this will be the permanent room, but welcome. I haven't taken roll yet, so yeah, just find a seat. So that's that. So yeah, you might see information about this. That's what that is. If anything, again, that would just be like bonus, and I would just want feedback from y'all or online. I don't know if anybody's joining online. If you are, say hi. But yeah, just kind of like a bonus thing, kind of help me like develop this course because I do want to develop it, and I kind of said with the state of Oregon, because Oregon's always promoting like open access resources. So I was like, yeah, I want to do this. I want to rebuild this. And my open math is just, it was, it's never the smooth like process of talking to each other. All these like, I don't know if you guys have been to other schools or use like Canvas and Blackboard and other things. They like all do not like to talk to each other. And that's what I was trying to move to my open math because that's more universal, but yeah, it kind of is what it is there. Anyways, so then let's look at, because I'm sure you guys want to know how your grade will be calculated. And I don't print out the syllabus. I just don't like wasting paper. But it's pretty self-explanatory. So now I'll have to change this. So yeah, we'll probably be in this room. Are you guys bothered by the high-pitched sound, or is it like only me that hears it? Yeah, so you kind of hear it. So maybe we'll try to search for a room, because I think they have this room labeled as like a Zoom room. So I don't know if we could switch or if that would be too much trouble. But yeah, I just kind of wanted to land here to get started, especially this first week, because I do like to do a few demos sometimes. And again, that's why I like need time to set up. It takes me a minute so I can bring you quality content. And then so kind of the format of the class and how we'll do it. So we have kind of lectures. So on Mondays, we'll lecture for like 2 hours. Usually we go 1 hour, take a 10-minute break so everybody's brain doesn't fry from too much chemistry and math. And then we'll finish the second half of the lecture. And then, like I said, we can do office hours after class. That's generally the best time. You know, get your questions in, go home. The other thing is, like, if you're at home studying, send me an email, right? You run across something in the textbook that doesn't make sense, send me a picture. Oh, that being said, textbook, this is why it's another big year change. We did change textbooks. I meant to bring the old one just to kind of show, because I really don't mind if you use the old one. Like, I'm sure people are trying to sell theirs. Let me see if I can find it quickly. So this is the old textbook. And so basically we're at the point, right, where like chemistry is chemistry, especially at the 100 level, right? We're very basic general knowledge. So any chemistry book will do. And again, this is probably like too much background information, but we used to run this whole series, Chem 104, Chem 105, Chem 106. And that's why we had this textbook to give you this overview of like OChem and biochem in like a 100 level format. But I think the nursing requirements changed. So no, nobody takes those classes. So I haven't taught those in years. And so the textbooks that we will be using, and it should be on the syllabus with a link, is this OpenStax textbook. And so this is where I'm going to, again, do some work to like try to coordinate, because right now all the chapters on the syllabus unfortunately go with the Janice Smith book. And so I need to kind of break up and kind of go through how OpenStax has it, because it is like a slightly higher level book. But again, right, chemistry is chemistry, and I'll give you everything that you need to know in lecture. Like, that's the goal. And so that being said, there should be lecture notes online. And so I just have the first week open. I need to fix this chapter 1 live link, so I'll get that going so you can like look at my OneNote and have that running. And so for those that ask, like, can I use my laptop? Like, yeah, that's perfectly fine to take notes on a laptop. And then the other thing about my course, and that it's open note, right? I'm not here to like quiz you on memorization of formulas. That's not really my interest, right? It's like, can we problem solve? And so that is also kind of fair for the online folks too, because we have historically a lot of people taking it online, and that gets into all these like proctoring issues, which make me uncomfortable. So it's like, let's just level the playing field and give everybody notes, and then that's fine. And then with ChatGPT and like AI, I'd say it's pretty hit and miss for chemistry. So, you know, like obviously don't cheat. Like maybe you can use it as a study tool. I have noticed, unfortunately, I don't want to admit it, it is like gotten better at doing chemistry and math. I used to be able to like feed it quadratics and it would get them wrong, but now ChatGPT is getting it right. But you know, again, just make sure you're learning, taking notes. You know, you don't want to cheat yourself out just by using AI. But yeah, I have the blank notes available. So this will be the format for every week, right? You'll have the notes. You can use them in a PDF format, and then also the OneNote if that works out for you. And yeah, question, like I would just stick to this OpenStax book unless you like really wanted this like OChem and biochem background information, but it's not necessary for the course. And this is the official textbook, right? So the official textbook is the OpenStax book. So like I said, everything is going to be based off of this book kind of moving forward. This just might be a weird transition quarter, so you might see a lot of old references. Like I said, I didn't totally fix my syllabus because I haven't gone through it like chapter by chapter in detail and like compared. But again, my notes are going to be kind of the accurate content, right? It's going to have everything hopefully laid out in a easy format. And then, oh yeah, back to grades. So homework. Grab it. I was late putting it out. So I put it out, homework, and then this week's lab. So go ahead and grab a copy. So if you're online, you should be able to turn all that in online, and then in person, right, you can do the in-person copy. I mean, it's the same homework. Or like I said, if you want to do the MyOpenMath stuff and do that like online homework and kind of compare and like give me feedback, like we can do all sorts of things. Like we can, like I said, we can figure it out. It's a 100-level chemistry course. The goal is to just kind of learn and have fun in here. So back to the syllabus. So blah, blah, blah. OpenStax is there. And then, so if you're online, you have videos that go with the lab. And then if you're in person, of course, we'll be doing those experiments. So that'll be a lot of fun. Goggles are provided, so you don't have to worry about that. I should have brought mine. I was running around like a crazy person. I will say that some people do like to purchase their own. Like, so we have the goggle style in lab, right, that stick to your face. And especially like men tend to run hot, or, you know, if you just run hot, then you start getting all sweaty. So like maybe, you know, if you want to purchase goggles, that's fine. Just kind of make sure they cover the side of your face there. And so that's totally appropriate to use your own safety glasses. And then we do provide gloves. So they're nitrile gloves, and then we do have neoprene as well. But we'll talk about that. Oh, I didn't fix this. So recitation went away. I'll have to fix this. This is kind of, so this is maybe where we could have some play, where I was saying, like, if you guys want to help me with the MyOpenMath stuff and help me kind of troubleshoot it and help me fix bugs, we could come up with a different percentage, because that was like my goal moving forward. Is I know people don't like exams and they can be stressful and too heavily weighted. So I wanted to make all these like modules, and again, like it didn't really happen, but we could play with this percentage of exam points and like drop this down to like MyOpenMath bonus. And so what I'm proposing is 2 different weighted scales, right? So if you're not interested in helping me with MyOpenMath, that's fine, right? This is your percentage here. But if you want to maybe play around, get some extra practice, or, you know, just get some percentage, I think I'll come up with like an alternative scale if people are okay with that. I'm kind of, like I said, I'm kind of feeling this out here as like an experimental thing, trying to make this course better as opposed to just like the same thing we've been kind of doing. So yeah, I think people are open to that. Blah, blah, blah. We're going to learn some stuff. No, I'm joking. And then, so every week we'll follow kind of the same format. So this first week we'll have the welcome quiz, so online people have their assignment. And then, so for our lecture on Wednesday, we're only going to lecture for an hour. And then we'll kind of stop, maybe take a break if you want, but then we'll have like a quiz. But this week we'll do our like welcome assignment check-in. It's like, you know, it's just like, why are you taking this course? And nothing hard, right? Like, tell me something about yourself. So that'll be this week's quiz. And then the subsequent weeks will be over the previous week's material, right? So next Wednesday will be over chapter 1, kind of based off of the homework and what we've done. And again, just kind of to prepare you for the exams. And then, yeah, so we follow that format. And then midterm week 5, lab practicum is only for the online, and then we'll have a in-person practicum at the end. So you'll have, I need to fix the syllabus. So yeah, you'll still have lab that week of exams, and then continue, And then, like I said, lab final will be in person for week 10 for the in-person class. And then, of course, there's 2 lab practicums for the online people. And then we'll have our exam on Wednesday in here. Or, you know, if you need to take it at the testing center, then by Thursday is when the schedule is. And then usual institutional things, so that's exciting. Any questions? Yeah. No, it's totally free, so you can just like, you should be able to Google it. Yeah, so it should all be on Blackboard. Yeah, you can look at it. All right, let me take attendance for the in-person people. Sorry if I can log in here. There's too many apps and things. And then I don't normally take attendance, right? That's only for the first week, so we can do add drop and make sure nobody is just taking the course to try to get money or anything like that. So let me find. Oh. Oh, and then, yeah, so for the in-person people, the benefit of me taking a long time with my setup is that I do have recorded lectures for you guys to go back and review. So a lot of people say that they like that, so you can always watch. Some people like to watch in class, or of course, right, if you're sick, you have to miss, or you got conflicts, kids, caretaking, whatever, you can always just let me know, hey, you know, I'm online today, and I mean, really, you just need to be in person for the labs, right? And then ideally quizzes. But again, we could work out stuff online since I teach this course online so much, so it's not that big of a deal. All right. So I will take attendance, and then let me know if you go by something else, and I apologize if I butcher names, and I might mute this for the stream just so we don't have everybody's name on there. So we'll be back after attendance. All right, back after roll call. All right, any other questions kind of come up or anything? Yeah. There probably will be, but I haven't set it up yet, so I'll email that out and talk about that. Yeah. Other questions? All right, so let's dive into lecture here. And So of course the first thing is, right, like what is chemistry and why study chemistry? And I often just like to probe people, like what are your interests, right? Like what are you pursuing? What are you studying? Yeah, anybody. So biology. So yeah, I feel like, to understand biology, you got to know chemistry, and then you can understand all the ion transport and everything. So I'll put a happy face. What else are people into? Watching the chat too. Yeah, history. What do you? Because that's pretty cool. Because there's so much like chemistry and like oil restoration, painting restoration. I don't know what you're into, or like I'm sure they can do toxicology sleuthing now with history. What do you have? Business management. So of course you can always manage chemical companies. Yeah, that's the other thing. Like, cosmetics is like always a growing industry, so you could like always get adjacent to that. Or I'll put business. Business is everywhere. Chemistry is also just like dinero and money. But what else do we have? Yeah, so chemical engineering. Where's our engineering here? So of course you got to understand the fundamentals of chemistry, how to engineer things. What else do we have? Oh, medicine in the chat. I was waiting for medicine. Yeah. And this is where I start putting like dollar signs everywhere. No. But I mean, big pharma is good. Many of the people I went to grad school with, right, they're working to develop um, all sorts of vaccines and drugs and making them, and I know people at like every levels, right? Like analytical chemists. So there's a lot there. What other interests do we have? So psychiatry, yeah, that goes with like medicine. I can't spell. And that always gets interesting. So now we 27 minutes until we hit chemistry, drug the class. No, I'm joking. But we do end up talking about drugs because obviously, compounds are drugs, and then how does it interact? Or, that's a big part of drug development too, right? Is crossing that blood-brain barrier. How do you do that? Um, what other interests do we have? Culinary. I love cooking. Where's cooking on here? Oh, food science. So yeah, chemistry is of course cooking, baking, ratios, everything. Or just getting a nice seasoning on a steak, Maillard reaction. So yeah, I love it. What else do we have? Also, if you can cook, you can do chemistry, so. Other interests. No environmentalist people in here? Kind of surprised. Usually there's somebody that likes the environment. The other thing I would say is like kind of all of these disciplines like medicine, biology, engineering. Like you can always think about patent law. That's a career that people don't always think about. So people that I went to grad school with ended up in the patent law business and pays pretty decently. You review patents or being a lawyer, right? Getting into like a very specialized science lawyer subject. But all that is to say, and this is why I really like chemistry. And of course, this is biased. I'm biased, right? Your textbook's biased. But a lot of people consider chemistry kind of central, right, to a lot of these subjects. It's related to everything. We kind of have to learn the fundamentals of the atoms and what we're made out of and everything kind of fundamentally how that works. We'll get like a tiny taste of atomic orbitals, but all that, right, gives us our macroscopic world and then all these interests that you guys have. So, I think it's really beautiful, and I just see kind of molecules everywhere, but. And so then just formal definitions now. So chemistry, of course, is defined as the study of matter. And Right. Oh, the other thing is like, please raise your hand and slow me down if you need to. I just kind of keep going sometimes, and I don't know where everybody's level is at. I assume that most people haven't taken any chemistry, but kind of slow me down if you need anything explained. Right. Like that's the point of this class. And sometimes I get excited anyways and talk fast. So matter is anything that has mass and takes up space. So of course air, solid, liquid, gas. And then matter can change from one form to the other, and we'll be looking at that. And so of course we'll look at chemical changes, and I'm sure you guys are familiar with chemical reactions. Burning, combustion, anything is lighting a candle, right? That's burning. Iron rusting, right? That's also something we see kind of daily. And then physical changes, we'll look at that as well. And of course, right, matter does not lose its identity. And we'll look at this in more detail, but just kind of thinking about what we see, right? We are lucky to see water in all three states of matter throughout our daily life. So just kind of thinking about what that looks like. Our solid ice, and then right, you take it out of the freezer, it starts to warm up, becomes liquid, and then right, you could take that liquid, stick it on the stove, start boiling some pasta water or something, and then you make steam, right? So just kind of thinking about those phases of matter. It's kind of putting us in the frame, right, mindset for the class. And so again, this might be a little bit of review, but we have to lay our foundation. So we have the classification of matter, and we're only going to focus on, right, solid, liquid, gas. I know there's plasma, right, but that just like exists at fringe cases of lightning, and so we're not going to talk about that, right? That's like more research oriented. And so, right, we have our three states, of course, so whether it's a solid, liquid, or gas. And so this is a preview, but we'll later learn that we can indicate our states of matter in a reaction by S, L, or G. But again, we'll see that again. And again, based on what properties it exhibits. I'll have to move a periodic table in here. So again, that's the issue with the last minute change. Oh, there is a wonderful online periodic table though. Let me pull it up. So P table is my favorite web periodic table. We'll see why later when we look at electrons and stuff, but I don't want to confuse people on day one. But what's nice about this, so this one is very marked up, which I kind of like. So as you look at different periodic tables, and I want to say it's like week 3, we'll look at different ways to kind of arrange it, but there's many different categories, right? Metals, nonmetals, metalloids, so we'll kind of look at that. But I like this periodic table. It makes it really easy to see kind of what's what. Everything's in color. And then we also have, right, our elemental forms of things. So everything that's black is a solid, right? And you can highlight that, so that's nice. Everything that's a liquid in its elemental form is blue, so mercury and bromine. Then gases, and of course this is just for our elements, which we'll get to what they are exactly. But other substances, right, you could also of course indicate, right, like isopropanol is a liquid, so just other substances. And then we can also classify it by its composition, which we're already starting to tease, right, because we saw elements there. And so those are going to be our fundamental atoms, which we'll talk about. And so looking at our states of matter, though, so back to that. So solid, and when something is a solid, the particles are tightly packed in a fixed place. And so solid, right, we usually say it has a fixed volume and fixed shape. And so that being said, right, there is still some sort of molecular motion, right? The electrons still moving around, they're still vibrating. They just can't slide past one another, right? So they're still fixed in position there. But then if we give it more energy, so I'll put either plus energy, or sometimes you see this triangle symbol, so this means heat. Or again, we can add energy. Uh-oh. Sorry. Something might be off with the stream, but I think the internet might be struggling. We'll see. And then, so liquid, right, we give it enough energy now. And now they can start to slide past one another. So maybe I'll say can slide past. And so now we can say, right, that it has a fixed volume. But of course, right, it takes the shape of the container. And so I'm sure you guys know that, right? You guys have poured water before from one container to the next. You know that it can fill any container. But of course, right, again, we can't compress the liquid. So that's the key point, right? You can't compress your liquid. And then, so then we continue to add energy or heat. And then, so now, right, they start to get farther and farther apart. And you can kind of think about that, right, when water is boiling, you're adding energy to it, and you can, right, see the steam rising, so you can see those molecules getting further and further apart, essentially. And so now we say we have no fixed volume, no fixed shape. And then the term that I often use is that they are compressible. And then, right, sometimes they can go back down to a liquid. So, right, we can compress them so far down. And so I would kind of think of like liquid nitrogen for this. So I don't know if you guys fill your car tires with nitrogen these days. But, right, you have your liquid nitrogen, so your nitrogen. And of course, 78% of the air is nitrogen, but you can compress that nitrogen down, right, all the way, cool it, get it to its liquid form. Now you can transport it around, right, put it at like Costco, I think, has a bunch of nitrogen. And sometimes you see those big nitrogen containers chained up. And then, of course, right, open up the valve at the appropriate pressure, and now it's gas expanding to fill your tire, or if you let it bleed out, right, the room and everywhere. And then again, right there, widely spaced, so again, compressible. Questions so far? Just kind of letting people catch up. Plus, I'm not sure if the stream is healthy. Usually my Wi-Fi is okay, but sometimes RCC Wi-Fi has issues, especially on like the first day of class. No. So yeah, you can't press solid. So same thing with liquid, right? Like you can't compress down a liquid. It's already in a fixed volume. So only the gas is compressible. Good. And then, so now we just have kind of the text that reiterates this. Oh yeah.
I've got a question about solid matter. So if you're not actually pressing down the matter, you're just pressing down the space in between, I guess, and getting the molecules like closer together. Because like that cardboard box, you could compress, right?
Yeah, well, I mean, then you could argue, right, that it has like air between it. So that's the thing. It's not like a solid. Yeah, well, I would also think of like solid as like sodium solid, where it's like, you can't really. I mean, I guess you can get technical with things that are like malleable and yeah,
Okay, okay.
but yeah, you generally can't compress it. Yeah, I don't know why this stream is going so poorly. I think it's just the internet, but I don't have a cable on me. Anyways, trying to find a hotspot too is another issue. All right, so yeah, like we said, our solid, they're packed tightly. And then again, they do vibrate, right? So there's still molecular motion. We want to make that clear. Later we'll talk, well, maybe I'll just tease it. So right, later we'll kind of talk about absolute zero, which is the complete absence of motion. And so that would be right when they do cease to vibrate. But again, right, so your electron is moving around, which we're going to get into. So your electron is running around your nucleus or vibrating. They're still wiggling a little. They just cannot move past one another. And so again, those are other solids. So diamond, aluminum, but I mean, obviously you guys can like roll out aluminum, right? So they're still like malleable, but we can't like shrink their volume. And then liquids, so again, right, they're easily pourable would kind of be, again, the distinction. And then obviously, right, we can do phase changes. So we could have gold, right, but then you heat it up. Well, now it's in the liquid state. So now it is pourable. So that kind of helps, right, your understanding. And so, of course, right, you heat something up, then it can become kind of more malleable, right? It'll start to move. So just kind of thinking about how a jeweler is going to like resize a ring or something, for example. And then, yeah, so liquid, again, we're referring to things that flow readily. So water, alcohol, gasoline. So all of those are substances that are liquids at room temperature. I'm sure we could think of others. And then again, like we said with the gas, so the gas is compressible, that key word there. And so thinking about it with a piston where you can really, change the volume there. All right, so then looking at this now, so now we kind of have this tree, right, of how we classify our matter by its components. And so we kind of have to go through this flow chart. And so, right, we look at our matter, and you have to determine is this one type of particle or not. And then if it's a pure substance, so this is where I would say, right, you want to get out that periodic table. Oops, not streaming tips, sorry. Too many windows already. So, right, if you're unsure about a substance, like people often get confused with like brass, for example. Like that's an alloy, right? But you may not know that. Like I don't expect you to know all these things. So the first thing you'd start off with is, okay, is this anywhere on my periodic table? So that could be a clue, right? So all of these things are then our elements. And so those are our elements on our periodic table. So let's just make that clear. So right on. Oh, and I know what other thing I forgot. I meant to print out. I'll print you guys out nice periodic tables for Wednesday. So you can have that. And so then we have, again, our elements. So they're one type of particle. And then we don't want to get confused by what are called allotropes. So let's look at some allotropes here. So if we look over, so for example, sulfur, there we go. Links to the Wikipedia here. So sulfur is an element, but sometimes when you see it, let's scroll down. Where's its structure here? There it is. So sulfur is commonly found in this weird cycloocta structure. So right, it's an 8-membered ring, and then it's just in this funky shape here, right? But we would not consider this a compound, right? So you don't want to get confused. And actually, let's back up for a second. And so let's define what an allotrope is. So anybody know any other allotropes or examples of allotropes? Or what might be, if S8 is one? I don't expect you to know. Just so allotropes, I'll define them, are different geometrical arrangements of atoms. So we looked at S8 being in the ring. And so other allotropes, so the famous one is going to be carbon over here. So let's look at carbon. And so let's go to our carbon allotrope page. Hang on. That's also why I like having extra time so I can pull up all these. Seriously? That's what I get for not using Google. All right, so these are kind of the well-known examples. So again, different geometrical arrangements. And so A, you could maybe guess, so this is diamond. And so diamond is known as a tetrahedral arrangement. So you can kind of see that in this picture here. So each carbon has a tetrahedral center, and then it's just repeating tetrahedral units over and over. So that's what makes diamond incredibly strong. And then if we look over at this picture of B over here, so this, anybody can guess what this is? So it is honeycomb structure, and so it's graphite. But what's cool about the honeycombs that you notice, so this is, and we won't really get into hybridization, but we'll touch on geometry. So this is a tetrahedral geometry, so technically sp3 hybridized. And then notice that this is sp2. And so each center here is trigonal planar. You can kind of see that. But the whole point is that it's flat, right? So the geometry totally changes the properties. So B is graphite. And so now we can see how your pencil works. And so these little layers, right, sheath off. And of course, that's what you leave behind on your paper. And that's why, again, it can kind of sheath off because it's pretty weak bonds in this direction, right, in this up-down direction, and then stronger across there. So graphite has some interesting properties. And then, let's see, I actually don't know what C is by heart. Oh, so this just Lonsdaleite, so it's probably just a different rock formation. But then this one is pretty famous, D here. So this looks like a soccer ball, and so this is C60. So this was the buckyball, I think discovered in the 90s now, but this was like a huge discovery back at Rice University, so they got the Nobel Prize for this. And later that led to the whole nanotube development. So first they made the buckyballs, and then they started making these nanotube structures where they're growing, right, little graphite-like structures. So that's like a whole vein of research now. And then let's look at the other ones, what they are. So, right, again, there can be a lot of allotropes. So I don't expect you to kind of name or know them all. We're just, again, kind of appreciating, yes, these are all still considered elements, though, right? So even though they technically have formulas, so, right, like, for example, the buckyball is known as C60, it would still be considered an element, right? Because it's the same element. And then we have, right, fullerene and amorphous carbon. But again, right, that's all just to say, okay, we can have different geometrical arrangements. So another element with allotropes that we'll go over, and then we'll kind of move on, is phosphorus. And of course, this is kind of famous. Maybe I'll just look up the And so, of course, people know white phosphorus, right, from war, and it is still used in war currently. That's fine. I mean, not fine, but anyways, we won't go there on the ethics of chemical warfare today. But I mean, unless you want to, but that's a rabbit hole. But anyways, the whole thing is it's just an allotrope. So again, different geometrical arrangement of phosphorus. So it's just phosphorus, still just an element. And so this is obviously not a stable form. And then there are other forms. So this is red phosphorus. So this is apparently can be formed from white phosphorus. And then you have this violet phosphorus and black phosphorus. So again, just different geometrical arrangements, right? So it's all in how they arrange, and obviously, right, that gives it its reactivity. So that's kind of what we want to go for in the class, at least, right? Again, kind of laying down a foundation as well, like why is diamond unreactive? You know, why is white phosphorus reactive? That sort of thing. Just kind of looking at our geometry. All right, so I'll write our notes. So again, carbon, I'll just put down examples. So we said diamond, C60. So again, all elements, graphite, those are the common ones. And then I'll put phosphorus, again P4, so white, red. And so this is not all inclusive. I just kind of hit the highlights of the main allotropes that you guys have probably heard of, but I'm sure there are other allotropes. Oh, that's the other either fun thing or wonderful thing. I mean, some people find it frustrating, I think, and like why people don't like chemistry is like, you know, chemistry has rules, but then there's always like an exception. And I mean, we kind of won't get into why all that is like atomic orbitals, yada, yada, yada. But I think that's like the fun thing about chemistry is like we can't always speak in absolutes, right? Or you can always go find something. There always is new research. Like, I could pull it up to share, but like there was just a new copper sandwich compound made that had never been made before. So there's always new breakthroughs. And previously, I think I said that silicon, I mean, I used to teach it, right? That like silicon can't make this ring structure. Well, I'll have to pull out the paper for y'all, but they just made a silicon ring structure finally, right? So chemistry, and like that's the beauty of chemical research, is like they're always trying to push the boundaries and get kind of creative with chemistry. But anyways, again, that's why we'll lay the fundamentals, but definitely ask questions, right? Chemistry has a lot of exceptions. There's a lot of funny things that go on, but usually I can kind of explain the why. All right, so then now we get into our other example of a pure substance, which is a compound. And so a compound, does anybody know the definition of a compound by any chance, or examples of a compound? Yeah, water. Or H2O, which maybe gives us a hint as a definition as to what a compound would be. CO2, excellent. You guys know your compounds. What else? Or maybe we'll define it. And so, right, you gave out these formulas, and so that's what you're giving me is a defined chemical formula, right? Some sort of given ratio. We could also, I'll add to that NaCl, table salt, or at least, actually, no, I can't remember if they use, sorry, no, I just went crazy. Because, right, if you have iodized salt, I think it's a potassium iodide, if I remember correctly. I can't remember if it's the potassium salt or sodium salt they use for the iodide, right? Because you need a little bit of iodide in your diet. But yeah, define chemical formula, and this is where we get into drug, the class really quickly. But do be cautious of drugs. So I would like, especially when you're learning, like that's why the internet is great, right? Because you can look this up and like, is this a defined chemical formula? And so let's see if I can think of a good example. So for example, if I could pull it up fast enough, or, oh, yes, I remembered correctly. So the example that I was thinking of like where people can get confused and where it's good, again, like use your resources for studying. Like chemistry is a lot, right? Chemistry is always evolving. But we don't want to mix up mixtures, right? And so I pulled up, so I don't know if you guys are familiar with like Norco, right? So Norco is just a drug. So sometimes you get prescribed it. And there's all sorts of drug mixtures. Oh, come on. But right, usually, so maybe this name is kind of older, but that's just what I was kind of thinking of. And so Norco is usually referred to as the combination hydrocodone acetaminophen pill, but that's not a compound, right? Because that's then a mixture of two things. And so that's why I would use the internet, so then we could look up hydrocodone. But now I just want hydrocodone. And so now we have, okay, there's a chemical, right? So it's like a discrete structure. And then it has, where's our formula? A formula. So that's always a key point, right? Is like you should be able to look it up and find an exact formula, not like a ratio of something. The other one that I was kind of thinking of, although it always takes me a while to pull up the ingredients, are like those Alka-Seltzer. Apparently I can't even spell. Okay, Alka-Seltzer, cold and flu. So this would be another example of a mixture. And so now we're kind of getting into our classification. And so you can see that this Alka-Seltzer cold and flu thing, it's a mixture of a whole bunch of compounds, right? So we have acetaminophen, so that's a compound. Dextromethorphan, so again, we could look at that and notice it has like a counter salt on there. Deoxyamine succinate, right? Again, phenylephrine. So it has like at least 4 different compounds plus whatever other inactive ingredients, right? So that's a whole mixture of things. And again, we can compare it to like aspirin, I think. So aspirin, right? Define chemical formula. So just things to keep in mind there. So I'll put aspirin, so hydrocodone, and then, so homogeneous, I'll put Norco medicine, or our Alka-Seltzer. All right, maybe let's just finish up this little bit. And we can kind of come back to it. I just wanted to give y'all a break because I know we've kind of been going for a while. But then we're at this last part of this heterogeneous mixture. And so we have this mixture, and we kind of skipped, right? And well, let's look at our two different types of mixtures. Well, our mixture is either a heterogeneous mixture or a homogeneous mixture. And of course, a drug should be a homogeneous mixture, at least, right, if it's a well-manufactured drug. So that would make sense, right, that you should be able to split the pill and it's an even dose. So that would be a homogeneous mixture. Or obviously we have other examples here like tea or anything else that just kind of looks the same, right? Like I always think of, and I'm kind of thinking of food, but like the first bite is the same as the last bite. So I'm thinking like Gatorade as well. We could even do like, vanilla ice cream. That's pretty homogeneous. But then heterogeneous, they always give this like wet sand. But other classic ones are like Italian dressing, or if we're going with the ice cream, I always pick like cookie dough, right? So you have one bite that's like full of cookie dough, maybe one bite that has no cookie dough, but just kind of not uniform throughout. So I don't know if anybody was thinking of any heterogeneous mixtures, other examples. Yeah. Oh, I wouldn't know the reason. Yeah. I mean, I think you could pronounce it homogeneous as well, but usually, like, I'm used to homogeneous. But other burning thoughts? All right, let's give y'all a little break. So, yeah, I mean, let's take a 10-minute break roughly. So, like 2:10, and I'll put a little be right back thing. So, yeah, take a little break. All right. Do we? Oh, yeah, we all made it back. Everybody make it back. All right. Any questions come up? All right. So yeah, just kind of reviewing that is again, right, we had our pure substances, so either an element where it's again, right, you're just starting out, so look at your periodic table. Oops, forgot to take off my break time. Look at your periodic table, right, double check it. I don't expect y'all to know everything right away. And then, right, same thing, compound, define chemical formula. If you need to look it up in Google while you're studying, I encourage it, right? You're supposed to kind of, you're still learning, like, that's what's expected there. And then we went over, so heterogeneous. Again, I would just say like first bite is different than the last bite, or again, different samples where you sample matters type of thing versus homogeneous or homogeneous, however you want to pronounce that. Again, it should be uniform throughout. So first bite, same as the last bite. So and then blah, blah, blah. So text. Oh, and then, uh, well, this always reminds me of a famous quote. No, it's not really a famous quote. It's a famous quote from my one of my advisors early on. This is my undergrad advisor. And he would always say, "My 3-year-old can mix things together." What makes a chemist, right, is being able to separate, distill, purify, actually get, a nice compound out. And so that being said, one of the most simple methods of purification is the distillation. And then I always point out that this illustration has a huge safety hazard. So this is not generally done anymore where you would distill with an open flame. So now there are like heating mantles that, just heat up using electricity, obviously, and that doesn't have an open flame. And so why you don't want an open flame is like, let's say you're distilling like ethanol or something. And usually this illustration, I don't think is quite accurate to your equipment because usually you have some sort of joint here. And so you have, right, a potential area for leakage. And obviously if you're using an open flame, now you have fire danger. And then obviously an open flame isn't generally safe, but that being said, we still use an open flame for like the flame test, which we'll do in lab. But anyways, you don't distill with an open flame. But the idea of distillation is you heat a substance up, and so maybe go at the lower boiling point, heat off that lower boiling substance, and then it rises. This is a double jacket here. So you have this inner tube where, again, let's just say you're separating ethanol and water. So the ethanol could travel up and then be cooled down by the water jacket here. So then you have this hooked up to a sink, cools down, and then you have pure substance. Or, you could purify water if you're on a island like that, right? Come up with some sort of jerry-rigged distillation setup. And then this gets into, I should just pull up a picture instead of trying to draw something out. Like how they separate out diesel is, right, like you take the crude oil and no, that's like a very small fractionating. Yes, this is what this is an industrial fractionating column. So, right, you take your whole crude oil, it goes into these huge fractionating columns, which basically have different temperatures, right, at every level. And then you have your high boiling stuff, low boiling stuff. So high vapor pressure, gas, right? Gas, different elements can be collected out this way. I think like helium is mined through this as well, if I remember correctly. But lots of different elements are collected, right, through crude oil, and it's all separated out through a fractionating column. And then, of course, the heavier things are going to be like diesel or, I think, kerosene. So that's large-scale distillation, especially for you chemical engineers in here. All right. Lost my sidebar. And so we'll get into again, right? We kind of have to lay our foundation. And so we'll get into units. But first, we'll get into, well, why do units matter? And so this is a little anecdote of what happened. And so this was back in 1998. They had the NASA Mars Climate Orbiter. And so, right, it was trying to land on Mars, but it came too close into the atmosphere and then burned up. And then, well, how did this happen? So, looking at it, so they found that the software that was calculating the force was uh, using pounds. And then the second piece of code assumed it was a metric unit. So mismatch of units, because different engineering teams, so it said that the Lockheed Martin team used pounds and the NASA people used metric units at the JPL lab. And so, of course, that obviously caused the mishap to happen and obviously was a very expensive mistake. So that being said, right, for our class, just make sure you label your units. So yay, right? And I don't mind too much. So some people like ask me like, what if I convert it? What if I do this? What if I do that? Like, as long as it doesn't specify, right, put this answer in grams, which you will have those types of questions in here. But otherwise, I don't mind, but just write down what the unit is so I know what we're talking about. And so that being said as well, so chemistry often deals with the very small and very big. So I often like to quiz people. I don't know if you happen to know like how big like a human hair is, what kind of scale. So it's a little bit bigger than that, but I like to guess. So it's a micrometer. So 1 times 10 to the negative 6 meters. So good. But all right, so what about sodium atom? And now might be. So where does a sodium atom fit in? Anybody want to take a guess? I was going to say now's the potentially the nanometer time, or so with there's also a special unit. So yeah, so size of the atom could be 1 times 10 to the negative 9 roughly, or nanometer scale, or kind of more accurate is chemistry has a special scale of angstrom, so the A with the, like this little 0 on top. And that means 1 times 10 to the negative 10 meters. So somewhere, again, you'll see kind of the units vary. So that's the other thing that, again, you should just kind of be aware of, right? Like turn your thinking brain on, make sure you're reading the units, because people will report things in meters or nanometers, right? Angstrom. So just kind of be aware. What about an elephant? Maybe like now we might think of mass or something with an elephant. But how would we measure it? What scale are we talking about? I was saying like mass. Yeah, so kilograms, right? And anybody guess the scale of how many kilograms an elephant is? Would you say 430? More than 3 kilograms? So yeah, like 3,000 roughly. So like 3,000 kilograms to I think like 5,000, kind of depending. Or you also have, right, the different unit of tons, but of course that's not a metric unit. And then, right, science of course can also deal with the really far. And so anybody know what the distance to the nearest star is, Alpha Centauri roughly? I think I might be off on my notes, but yeah, what do you say? Well, other than the sun, the other stars. Not that far. But yeah, so 4.35 is I think what I have light years, but I like that you use light years. And so right, that's just telling you how far things are traveling. So light years. So what does that mean again? So excellent. So yeah. So right, so I'll kind of remember that. So super far, right? So that's a long time. And then according to my notes, I have this as roughly as 4.17 times 10 to the 13, I believe, kilometers. So that's kind of ridiculous. Excellent there. You guys are on the ball with this. But yeah, so all that being said is, and of course I'm kind of using this already, right? Scientific notation to indicate really small, really large. So we're kind of all over the place, right, with science. So depending obviously on your field of discipline, right, what numbers you're working with. So this will be something else I'll print out for Wednesday. I'll give you this kind of cheat sheet here that you guys can fill in. And so we have, so you guys may be familiar with the metric unit. And so, of course, people say that the metric unit is superior to our like English system because it's based off of multiples of 10, which is, I mean, fair enough, but I don't know. I always make the joke. It's like I know what the temperature is in Fahrenheit, and I can tell you like the boiling points of all the solvents in Celsius, but I don't know what a hot day is in Celsius. It just doesn't feel right to me. But anyways, that's just what you know. But looking at our units, so kind of again what we're going to be looking at. So we have this special unit which we'll come back to, which is mole. And so this is used for chemistry, and it's a special quantity, which again I don't want to get into what that's defined as. It's kind of like a baker's dozen, but no, I've probably already said too much. Yeah, 6.022 times 10 to the 23rd. I just didn't want to go there. Atoms, but now we've gone there. So yeah, we'll put that aside. So back to base 10. So like and you can do right millimoles, megamoles, so that's why it's there. So right, like you can have millimoles, etc. But let's focus on these other ones. And so you're probably familiar with meter, right? Like, yeah, I'm sure you've seen a meter stick before. And then so the meter is a little m abbreviation, and then we'll see the prefix that we'll add. So your base unit for mass is grams, uh, and then your base unit for volume is liters. Temperature, I don't like that this has this as Celsius. I would probably put this more as Kelvin, because this is going to be thermodynamic base, but again, that's kind of already saying too much for day one. So again, we'll come back to that idea. And then we have seconds, of course. And then we don't really use information storage in here, but it's just kind of here, right, that you can add the prefixes as well to the bytes, right? Kilobytes, megabytes, gigabytes. So. And then we have, so multiples of 10 are created by adding a prefix to each unit base. And so this chart, and so what's kind of confusing, so you have to kind of watch what this is saying. So this, if we look at our chart here, so we have, for example, let's look at tera, right, and it has capital T, but then it says quantity in one base unit, and so it's tera to the base unit, so 1 over 1 times 10 to the negative 12. But to me, this is kind of confusing. when they have it this way. I prefer when it says it like this, that there are 1 times 10 to the 12 meters and 1 tetrameter. Or I like this page better. And then we'll work on, like I said, writing these conversion factors out so you have these notes, right? So that's my intention, is that you kind of have these notes. We're going to establish these conversion factors and what they mean. And so for this one, the multiplier is by the base. So this means, and I like putting units on just so we can kind of, again, have a frame of reference. So there's 1 times 10 to the 12 meters, right? And I don't know, in 1 tetrameter. And then for our conversion factor, so let's step back for a second. So again, this is quantity in 1 base unit, but it starts to confuse me down here. I, again, prefer a multiplier like saying milli. So this is, again, by the base, so 1 times 10 to the negative third. And then, okay, but what are we talking about when we say conversion factors? And so our conversion factors are just our expression. And I find it's often helpful if we think about our conversion factor in like American units, like we have 1 foot equals 12 inches, right? That's a conversion factor. And then the whole point of this conversion factor dimensional analysis setup, and I will kind of write this out formally, like I know that there's other ways mathematically to get there where we can use proportions. Some people can just kind of like do it, right? But I'm going to set up the dimensional analysis so it kind of makes sense with like our railroad tracks, as we call it. And all that is setting up that you can kind of write your conversion factor in this way, like if you were going. So now we can start to set up kind of our railroad tracks. So let's say we said convert, and let's just make the math easy. So 24 inches to feet. We have our conversion factor, and again, it's just a relationship. And so now we can say, okay, I want to convert inches to feet. I know it's pretty easy on this one, but now I'm setting up dimensional analysis. So what I start with, and then the whole point of your conversion factor is to have a relationship that you pick where such that the unit that you want is on top and then the unit that you're canceling out is on bottom. And again, I know it's pretty simple right now, but I think it's better to work through this simply and see that, right? So now we have, okay, well, that's how my inches will cancel out. And then we could do some mental math here. I will pull up my calculator. So I do have a fancy calculator. But of course, you could probably do, right, 24 divided by 12. So then that gives us 2 feet there. And again, with our proper unit. And so the conversion factor will just help us convert accurately. And then once we get to like stoichiometry with more steps of calculations, that's why I kind of suggest using this dimensional analysis or railroad track method if you've ever seen that in high school before. Then yay, calculator. And then I could probably give you a link to this virtual machine. So this is obviously like a virtual TI-83 machine that I run. Otherwise, you're open to kind of use whatever calculator. I forgot to say that. But so use whatever calculator you're comfortable with, but you probably want one that can like do logs. I mean, we don't need to do too much in this class math-wise, but I mean, you still got to be able to punch and do calculations. And so kind of going forward, you want to make sure you have like the calculator that you want to use on an exam just so you can practice. And I don't mind if that's a phone calculator necessarily. I just don't want to go into like chat GPT territory, right? If that makes sense. Like that's fine if you use an online calculator, but don't be having chat GPT do it. All right. So then, and again, kind of stop me if this doesn't make sense. Uh, but all we're trying to do with our conversion factor is come up with our relationship that expresses, right, our same value in different units. And so this is another relationship. So now we can say we have 1,000 millimeters in 1 meter. And again, right, you can just write this two different ways depending which way you're converting to. So then what we want to do, and like I said, I should have printed out these sheets. Uh, but we want to write our relationship so we can practice. And so there's like kind of four different ways we could write out each conversion factor. So me personally, I like using positive exponents at all times, right? Negatives are fine, but you just got to remember all the rules, or of course plug them into your calculator directly. So our conversion factor for this one would be, of course, 1 times 10 to the negative, or sorry, 1 times 10 to the 12 meters is 1 terameter. We could write that flopped, right? Sorry, that's a bad M. That looks large, is 1 times 10 to the 12 meters. Or if you want to write it using negative exponents, so this is maybe where this one will help because this is how many are in the base unit. So then we're saying 1 times 10 to the negative 12 terameters is 1 meter, right? So that's what that means. So same thing, right? And again, we can express that with either one on top or bottom, just depending which way we're going, right? Which unit we're converting to. And then this is just so you guys can kind of see the math. I'm not sure where everybody is, so that's why I'm trying to show this explicitly, right? So then we can go from one to the other by multiplying by 1. So if I multiply by 1 times 10 to the 12 over 1 times 10 to the 12, we get back 1 terameter is 1 times 10 to the 12 meters, which is what we'd said. Okay. Hopefully this is easy. Some people are kind of looking like this is easy. So like I said, I don't know like where people are at. So I would say let's take a second to fill out this chart. I wonder how long it would take me to run and print it. Should I run and print this chart? Would that be helpful? Okay, yeah, let me do that. Maybe you can start like mentally doing that, but I think that would be a good thing to have is all these conversion factors like on a chart. You can write it out, like make sure you understand it, and then we'll do some practice. I apologize. So let me print that out. I should have thought of that. But yeah, I think that'll be helpful. So I'll be right back. All right. Let me mute this. But yeah, let's take some time to kind of go through, write down what they might be. I can kind of come around and help people if you have questions. But yeah, we want to get our conversion factors solid. So then this is like your notes for, like I said, quizzes, exams. Like I want you to use your notes. I don't want this to be a memorization class. Like that's my goal. It's a problem solving learning class, not just straight memorization. And then, yeah, if you need to sneak out, that's fine. You know, that again is a good thing about posting the lecture is you can catch up with what you miss. Uh, and always, you know, just kind of do what you need to do. Oh, yeah, sorry. So you can see the example there. So there's one example. But yeah, like I said, you can flag me down and I'll come say hi or help. I'll start writing them out. It looks like you guys are getting it. It's kind of hard for me to gauge the first week though. But again, don't be shy to ask questions. Like ask away. And then I was telling people, right, you don't necessarily need to worry about the negatives. I'm just kind of putting it there. But me personally, I just like the positive conversion factors. Like I said, I don't like having unnecessary negative signs. Oh, we did leave off like deca from this, so just keep that in mind if you run across that, that you don't have everything on there. And then so also watch out. So now we flip right from kind of this positive multiplier by the base unit to now this negative multiplier by the base unit. So again, you just want to keep in mind what that means. And I like keeping it in positive exponents. So now we're saying there's 10 decimeters, right, in 1 meter. Or 1 meter is 10 decimeters. And notice that's deci. And then again, or by the base unit, we're saying 1 times 10 to the negative 1 meters is 1 decameters, right? And again, you can flip that expression there. So same with centi. So I just like being in positive units. So again, this is by the base, right? So we're saying 1 times 10 to the negative 2 meters is 1 centimeter. But that's not as intuitive to me, so I like saying 1 centimeter is 1 meter. Yeah, question. So we have, and let me just double check it. So yeah, deca, and so that would be, let's squeeze that in if you want that as an aside. So deca, so DECA would be our abbreviation, and so 1 decameter is 10 meters there. So this isn't commonly used, but I feel like it crops up somewhere, so I just want to make sure that you have seen it. And of course, I'm sure this goes on. So again, not all inclusive, but this is what we'll see in class mainly. And so we can keep going. So just, I guess that's mainly what we'll get to today, although I would like to do one conversion before we go, but we'll see. So again, just writing out your conversion factors. So this one's done. So 1 times 10 to the 6 micrometers is 1 meter. And notice the micro is that weird mu symbol. It looks like a U with a tail or something funny. So that's micro. Nano. So I'm just going to keep writing them out. Did we have questions about these though? Um, so again, I like the positive one, so that's why I wrote the positive one here, right? So I wrote the negative over here, but it's by the base unit, so let's do nano, right? So what this is saying, it's by the base. So 1 times 10 to the negative 9 meters is 1 nanometer. Or again, we can write that in reverse. But I don't like negative exponents, so it's the same thing as saying, so mathematically you can multiply it by 1 times 10 to the ninth, right, and get rid of this. But then that gives you, and just think about it, okay, there's a ton of tiny units in the big unit. And so, and that's always like the other thing is like always try to sanity check yourself. So like after you do something like, does this make sense, right? Like which way are our units going? And so our conversion factor, right, you have 1 times 10 to the 9 nanometers. Okay, that means I should have a lot of the tiny units in one big unit, right? And so I would always stick to the positive exponents personally, but like, you know, you're more than welcome to use them. Like mathematically, it's all the same. just as long as you understand like when to use them. And at the very least, you can like write down the conversion factors you like in here and then just kind of pick them, right? That's kind of the idea. I'm trying to make this as easy as I can for unit conversion. And again, femto, super, super tiny. Uh, Ahmed Zawel, he was an Egyptian chemist. He did some work at Caltech, but he got a Nobel Prize, I don't know how many years ago now, but he did like femtosecond laser experiments, so incredibly fast. So again, tons of tiny units. So 1 times 10 to the 15. So in his case, it was femtoseconds. But of course, I like meters, so I just put femtometers in 1 meter. So again, super tiny. A lot of the tiny units in your big unit. And then I'll continue filling out. So it looks like we've run out of time for an example, but we'll pick back up on Wednesday with that. And then we will have lab, so I should see everybody in person for lab on Wednesday morning, so 9 a.m. So it'll be 312, kind of like over there, like across the hall from where we're at. And then this should be our permanent room, so I'll probably make an official course announcement in case we lost somebody along the way. But yeah, I think this will be our room for the rest of the quarter. Unfortunately, it's pretty tight. I will ask about the buzzing, although I feel like it went quiet now. But yeah, I might ask about that. All right, any other comments, questions? So yeah, just try to get this filled out. Oh,
And so when do you want the homework done
oh,
by?
so homework is usually due the next week. So ideally on Monday, but you'll find that I'm like pretty flexible with deadlines. Like I understand life happens, you know, blah, blah, blah. But try to keep on pace with the course. So turn in the homework on Monday, but again, plus or minus a few days. Any other questions? I was just ending.